Heat of combustion. So, heat of combustion is a great deal like heat of formation. Okay. So you have some substance, here X, you combine it with oxygen and you produce the results of combustion. I call them oxides because they are things combined with oxygen. Huzzah! Okay. Now we're usually talking about hydrocarbons, methane, ethane, propane, carbon and hydrogen, hydrocarbon, yeah. So the results of combustion are usually CO2 and H2O. Okay. Now, just like heat of formation, it is normalized so that we only have 1 mole of the thing being burned. So we'll have fractional coefficients sometimes on the oxygen. Remember, heat of formation, we make 1 mole of the product, 1 mole of the thing in question. With heat of combustion, it's 1 mole of the thing being burned. So here's some examples of heat of combustions. We have cyclohexane, C6H12. When you burn that, it requires 9 moles of oxygen, makes 6 moles each of CO2 and H2O, and heat of combustion is 3920, negative 3920. So heat of combustion is very simple, very straightforward. It's just normalized to the thing being burned. Okay? That's really all there is to it. And beyond that, we treat it just like any other heat of reaction, except for the fact that it gets, special dispensation to have these fractional coefficients sometimes. Okay. Heat of combustion is really simple. There's not a heck of a lot to it. Don't even know that it'll be on the test, but it is. It's mentioned in the textbook, so I figured I would go ahead and mention it here. Okay. All right. Now let's go on to something a little bit more complicated, specifically spontaneity. Okay, spontaneity isn't too bad in and of itself. Okay. Spontaneity is the term we use to talk about whether or not something happens. Okay. If a process happens without outside force, then it is spontaneous. If the process doesn't happen without us forcing it, then it is non-spontaneous. So, spontaneity is dependent on your conditions. So, liquid water freezing to ice is spontaneous at negative 10 degrees Celsius. You expect that to happen. It should be next week sometime, I believe, Desiree. The lab final should be next week. At positive 10 degrees Celsius, water freezing is non-spontaneous. You don't expect water to freeze. Okay. Wood burning, the burning of wood, is spontaneous at all temperatures. You have to start the process. That's activation, not spontaneity. Okay. The reaction continues all on its own. You don't have to do anything to keep it going. Okay. So, sometimes there's a barrier in between in between a reaction and and the reaction going, right? That's activation energy, whether or not the reaction starts. But a spontaneous reaction will happen. It'll keep on going once it's started. Okay. So if a reaction is spontaneous, in the way it's written, then it's spontaneous. A to B, spontaneous. Fun. Fine. Great. Not a problem. If it is non-spontaneous, then it is spontaneous in the reverse direction. B to A. Okay. So if A to B is non-spontaneous, B to A will be spontaneous. And if it's not spontaneous in either direction, then it's at equilibrium. Okay. Equilibrium is when A goes to B at the exact same rate that B goes to A. Okay. You don't have equal quantities of A and B, but you have constant quantities. They're not changing anymore. Okay. So, going back to water freezing, at negative 10 degrees Celsius, it is spontaneous for liquid water to turn to ice. At positive 10 degrees Celsius, it is spontaneous for ice to turn to liquid water. At 0 degrees Celsius, it's at equilibrium between ice and water. Okay. Now, enthalpy, delta H, is not enough to determine whether or not something is spontaneous. You need something more. Endothermic reactions can be spontaneous. Remember Epsom salts, potassium chloride, I think that was. You dissolve that in water, that's a spontaneous reaction, even though it's an endothermic process. Water boiling is an endothermic process, but that obviously is spontaneous at high temperatures. Okay? Exothermic processes, like the burning of wood, those can be spontaneous as well. Okay? So we need another factor. We need something more to understand when and why something is spontaneous. And that is entropy. Okay. So that is what we will discuss in the third and final set of slides. Entropy. All right, so entropy is another one of those things that is kind of hard to define, just like energy and enthalpy and all that other stuff. Okay? In physical chemistry, you're dealing with a lot of really abstract things. Entropy is just one of those things. Okay? So, the second law of thermodynamics says that the entropy of an isolated system will always increase. Okay. Remember, an isolated system, nothing in or out, neither energy nor matter. The universe is the ultimate isolated system, so the entropy of the universe will always increase. Okay. And a mathematical definition of entropy is that ds, where S is entropy, will always be greater than dq over t. We have to use a swoopy d there, because it's a path function. Entropy is a state function. Heat is a path function. But entropy, the change in entropy for a system, is greater than or equal to the change in heat divided by temperature. If you're having trouble sleeping, go ahead and head over to the Wikipedia article on entropy and read various statements of the second law of thermodynamics. It is not a particularly fascinating read. Okay. But for an isolated system, entropy will always increase. Another way of putting it is that entropy is randomness or disorder. Entropy is possibility. Okay? The more freedom a system has, the more possible ways there are to arrange the system, the more the system can do without really changing, the greater the entropy is. So, if you have coffee and cream, unmixed, completely separate, that is a very low entropy state. You cannot swap any two portions of that without an obvious change. On the other hand, if you have the coffee and cream fully mixed, that is a very high entropy state. Okay? You can swap any two portions of the coffee mixed with the cream, and it'll be identical. Okay? High entropy. There are lots of possible ways of arranging the coffee. In this case, there are very few possible, much fewer, I should say, ways of arranging the coffee and cream in this case. In the middle, that is a medium entropy state. Okay? In terms of the universe, Coffee and cream unmixed, low entropy, that's the Big Bang. Coffee and cream fully mixed, high entropy, that's the heat death of the universe, trillions of years in the future. In the middle is when interesting things can happen. That's where we live. How fortunate we are. Okay? So interesting stuff can happen here in the middle when the low entropy state is proceeding to the high entropy state. Okay? Low disorder, very, very high order, very rigid. Okay? Very, very high disorder, lots and lots of randomness, high entropy. Okay? So in terms of physical processes, okay, remember entropy is about freedom. So increasing entropy going from solid to liquid to gas. The solid, the particles are locked in place. They can't move around. They can't do very much. Okay? A liquid, the particles are free to move, okay, but they're still contained within a particular volume. Okay, they're still crammed right next to each other. The particles are still touching. They're able to move. They're able to slip past one another, like a crowd in a concert, but they are free to move, so they have higher entropy. But it's not incredibly high entropy because they're still locked down in a way. Okay, they're still locked into a particular volume. But a gas is very, very, very high entropy. The particles are free to move. They're no longer touching. They can explore to the ends of the universe so long as a barrier doesn't get in the way. Okay? So solid to liquid to gas, hot increasing entropy. Gas to liquid to solid, decreasing entropy. All right. So for chemical processes, okay, you'll have to actually calculate it to get an actual number, but there's a rule of thumb, okay, for physical processes. Look for gas. More gas generally means higher entropy. Not absolutely always, but generally. Okay. So, combining hydrogen and oxygen to make water. Okay. We start with 2 plus 1 is 3 moles of gas on the left. We go to 2 moles of gas on the right. That's a decrease in the moles of gas. Therefore, we should expect a negative change in entropy, a decrease in entropy. Okay. Down here on the bottom, we have solid calcium carbonate decomposing to solid calcium oxide and gaseous CO2. We go from 0 moles of gas to 0 plus 1 is 1 mole of gas, an increase in moles of gas, therefore an increase in entropy. And here in the middle, we have methane plus oxygen, goes to CO2 and H2O, 3 moles of gas on the left, 1 plus 2, to 3 moles of gas on the right, 1 plus 2. 0, not really 0 entropy change, but a very, very low entropy change. Okay? So that's just a quick and dirty rule of thumb. So that we should expect negative entropy change for water, for the formation of water. We should expect a positive entropy change for the decomposition of calcium carbonate. And we should expect a very, very low, not actually 0, but very low entropy change for methane and oxygen to CO2 and H2O. Now, there's obviously more to entropy than just is a gas present or not, but it is pretty complicated to try and determine what the actual changes are. So in reality, we have to use math. Okay. So H2 plus O2 to make H2O. The entropy, not enthalpy, but entropy change for that reaction is negative 88.8 joules per Kelvin. Yeah. The units of S are joules per Kelvin. Entropy is kind of weird. Remember that the mathematical definition of entropy back here, the change in heat at that temperature, joules per Kelvin. It's just something you're going to have to get used to. The other thing you're going to have to get used to is that you have to be very careful about your units. Enthalpy, H, remember, is almost always going to be recorded in kilojoules. Entropy is almost always going to be joules per Kelvin. So when we start combining these, and we will be combining these, you're going to have to be very careful to get your units the same. One of these will have to be converted to kilojoules, or the other one will have to be converted to joules. Okay. Also, it looks like entropy is a lot lower than enthalpy, because, like I said, enthalpy is in kilojoules, but that's because you're dividing by Kelvin. And remember, Kelvin is an absolute temperature. So at room temperature, we're at about 300 Kelvin. So you multiply this by 300 and you'll have several thousand joules. So it is actually tens of thousands of joules. So anyway, the point is that it's not as small as it looks. All right. So calculating entropy for a reaction is very much, almost exactly the same, I should say, as calculating enthalpy. Okay, products minus reactants. Okay, you take your products and you multiply the numbers out of a table like this. You multiply by the coefficient. You add those together. Take your reactants, multiply by their coefficients, add them together. Then products minus reactants. Final minus initial. How did I do what, Desiree? Let's see, I was over here going backwards really fast. I was just using the arrow keys on the keyboard to move back and forth through the thing. All right. So for this particular reaction, we are it's the combustion of benzene. Okay, 2C6H6 plus 15O2 to make 12CO2 and 6H2O, liquid water. Now, we get those numbers right off the table over here. Okay, so this is entropy over here on the far right. Now, this table is weird because it records kilojoules per kilomole for some reason. But that works out to be the same as joules per Kelvin. Oh, the negative 88.8 joules per Kelvin, I did that math elsewhere. That or I looked it up. Yeah, almost certainly I looked it up or did the math. It's not too important. You'll be able to do it yourself in a couple of seconds because we're working through the example of how to do that. So for benzene, let's bring up our calculator. All right, we have 6 water, 6 liquid water. So 6 times, where's liquid water? Liquid water right here, 69.92. So 69.92. Plus, we have 12 gaseous CO2. CO2 right there, 213.80. So 12 times, what was it? There it is, 213.8. Okay, so that's the products added together. Now we subtract our reactants. We have 2 benzenes. 2 times benzene. Oh, well, 269.20. Plus, and oxygen. There's 15 of those. And here's oxygen, 205.04. Now, notice that there is not a 0 there. For enthalpy, or enthalpy of formation, pure elements in their native states have a 0 enthalpy. Notice all those zeros there. Okay, carbon, hydrogen, nitrogen, oxygen. Elements in their native states have a standard enthalpy of formation of 0. That is not true for entropy. you'll never have zero entropy. Well, there is the third law of thermodynamics gives us a 0 point of at 0 Kelvin for a perfectly ordered crystal. But for real substances at real temperatures, you are not going to have a 0 entropy. Okay? So that is something to keep in mind. Okay. So for the combustion of benzene, we're looking at negative 628.88 joules per Kelvin. Okay. Now, does that make sense? Well, we are going from 17 moles of gas on the left to 8, to that should be gas right there, to 12 moles of gas on the right. Either way, we're decreasing the moles of gas because we went to liquid water here rather than gaseous water. Okay. So products minus reactants, just like with enthalpy. Just got to remember that for elements in their native state, it is a non-zero number for entropy. So let's go ahead and real quick do water. Products minus reactants. We have 2 water gaseous. Where's water? 188.83. So 2 times 188.83. Enter. Minus parentheses. 2 hydrogens, so that's 2 times 130.68 plus 1 oxygen, 1 times 205.04 and negative 88.74. So that is how I got that number in on the previous slide. Products minus reactants. The water minus the hydrogen and oxygen. Just using numbers off a slide very much like this one, or out of the back of the textbook. The textbook has lots and lots of tables like this one right here, with enthalpy on one column, entropy on another column, and then something called Gibbs free energy in a third column. We'll get to Gibbs a little bit later. So let's go ahead and walk through the combustion of methanol. Okay. Methanol plus oxygen makes CO2 and H2O. We should once again see a decrease in entropy because we're going from 3, no, actually in this case we should see an increase in entropy because we're going from 3 moles of gas on the left to 6 moles of gas on the right. Okay. So methanol, methyl alcohol, liquid. Okay. What we're working with down here. So let's bring back up my wonderful guy here. So products minus reactants. Our products are CO2 and H2O. So how much CO2? 2 moles of CO2. So 2 times CO2 gas, 213.8. Plus, I believe it was 4 moles. Yes, 4 moles of gaseous water. So 4 times water vapor, 188.83. Close parentheses. Minus, open parentheses, 2 moles of liquid methanol. 2 moles of liquid, 126.80. 2 times 126.80. 3 moles of oxygen, 205.04. 3 times 205.04. So positive 314.2 joules per Kelvin, or joules per Kelvin mole. So calculating entropy is very, very similar to calculating entropy. Or enthalpy and entropy are very, very similar. Products minus reactants. You get the numbers off of a table like this, multiply by the coefficients, add your products together, add your reactants together, then products minus reactants. It's a lot of math, plenty of opportunity to make mistakes. I recommend I really strongly recommend you don't just do what I did. Do not just try to plug it all into a calculator and hope you can keep it straight. Write it all down. Write it out. Even on your test on Monday. Write it all out. Okay. Speaking of tests, don't forget that you have the retest for test 3 tomorrow. They moved it because of the storms on Monday. All right. With that, we're done with this set of slides. If there are any questions, I will wait for that. And that'll be it for today. Tomorrow, we'll finish Chapter 8, talking about spontaneity and Gibbs free energy. Practice, 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 practice. I will wait some 30 seconds for questions. Example questions? Yes, tons of those in the textbook. The textbook is full of examples. Remember, if you go into My Labs Plus and look at the, not the chapter outline, well, there is the, I can't remember what it's called. Not chapter outlines, but something similar. Chapter learning objectives, there we go. Has end of chapter questions. That is, those are good examples for you to check on. And not only that, but there are examples that they walk through, just like I walked through these there in the textbook. Okay. You can be asked to find the entropy of reaction. You can also be asked to find the entropy change for a specific amount of substance, just like anything else. But yeah, plenty of examples in the textbook. You can also, remember, as with anything else, Google is your friend. So, like something like this. Example, entropy problems, or entropy practice, or something like that. Okay, you got plenty of possibilities there. Scientists and science geeks know that these things are difficult. Okay. So tons and tons of stuff there. All right, and with that, we're done for today. We're almost done with Chapter 8. We'll be back tomorrow to finish it up with those last 2 sets of slides. And I will see you around.